All right, so this is 10.2. So this is the second section of chapter 10. We're going to talk about thermal expansion and energy transfer. So you just know from everyday experiences that when the temperature of something increases, the objects tend to expand. So things tend to get larger or expand when the temperature increases, and they get smaller or contract when the temperature decreases. Just think about this in your everyday life. When it's really hot outside, your fingers tend to swell and expand, but when it's really cold, they kind of shrink. So I know in the summertime, you can barely, on my rings, I can barely twist them around in the summer because my finger has expanded. But in the wintertime, they're always twirling around, twisting around because my fingers have contracted and are smaller due to when it's cold outside. So things in general expand when temperature increases and contract when temperature decreases. So if we think about the length of a rod when it's heated versus when it's cooled, the length changes. Now, the thing is, it changes by a proportional amount depending on what it's made up of. Okay, so we can determine the change in the length by multiplying it by a constant times whatever the change in temperature is. So the bigger the change in temperature, then the bigger the change in the length of the rod. And that proportionality constant lets you know that different materials will expand and contract differently. Okay. All right. All right, the constant of proportionality in this equation depends on the substance. So make sure you make note of that your constant depends on the substance that the rod or object is made up of. Iron has a constant, aluminum has a different constant, different copper would have a different constant. So it just depends on what that rod is made up of, what that constant is. So we're going to look at an example that shows how change in length with heating depends on the initial length of the object itself. All right. So when rod 1 is heated to a amount change in T, so it's heated by a certain amount, its length increases. So we have a change in the length, delta L. Rod 2 is twice as long as rod 1 and is made of the same material. So if rod 2 is heated by the same amount as rod 1, does the length increase by delta L, 2 delta L, or delta L divided by 2? Okay, so if we think about that conceptually, you imagine rod 2 is being composed of 2 copies of rod R, or rod 1, placed end to end. So that's what you have here and here. The same rod, same material, same everything. It's just this one is twice as long. So when your temperature is increased by the same amount, each copy of rod 1 expands by whatever the change in L was. Okay, so that means that this one, since it's twice as long, is going to expand twice as much. So the rod is going to expand 2 times delta L because it's twice as long. All right. So in the last example, we were just looking at change in length with heating depends on the initial length of the rod. So the longer the rod, the bigger the change in the length. Thus, thermal expansion of an object is proportional to the length and the temperature change, both. Because remember, our equation is some constant K times the change in temperature. So it's proportional to both the initial length and the temperature change. The constant of proportionality, that's that K value, relates the temperature change and the length change. And that proportionality constant is known as the coefficient of thermal expansion, alpha. So when you're reading your problems, we had another alpha a couple of chapters ago. Make sure you're reading your questions carefully. This is the coefficient of thermal expansion, okay? Alpha, not angular acceleration alpha, okay? So just be clear about that. Read your questions carefully. So the equation giving the relationship between the change in length and the coefficient of thermal expansion, initial length, and temperature change was going to look like this. Oops. Okay, well, that's odd. Okay. All right, well, let me write it in. There, it's not in there. So make sure you write this down somewhere. Change in L, change in length, is equal to alpha. The coefficient of linear expansion, coefficient of thermal expansion, the initial length of the rod, and whatever the change in temperature is. So that is the equation given in your book for the relationship between the change in the length, coefficient of thermal expansion, the initial length, and the change in temperature. The units of alpha are 1 over K, Kelvin K. Okay. All right. So there is a table in your book, and I'm just going to put the page number here. Page 351. There's a table that lists the coefficient of thermal expansions for various materials, various substances. Okay. So when you're doing your problems, you're going to want to refer back to that table on page 351 so that, because you'll need those to do the problems with. So thermal expansion plays a role in the functioning of several useful devices that we use. So a bimetallic strip, such as the one shown in the figure below, consists of two metals bonded together to form a single strip of metal. And so it's literally, and this is in your book too. For some reason, the figures in your book are not showing up in the PowerPoint. I don't know why. But page 352. And it's literally, you have a strip of metal, then you have a strip of another metal, and they are put side by side and bonded together. And that's what a bimetallic strip is. Just like the name sounds. Two metals bonded together. Okay? Oops. So what do we use these for? Since they're two different metals, they will have two different coefficients of thermal expansion. So the two sides of the strip are going to change length by different amounts, whether they're heated up or whether they're cooled down. And that will cause the strip to bend. Bimetallic strips are used in thermostats and thermometers. So your thermostat is the thing that turns the heat on and off. So depending on So they'll have two different metals bonded together. And depending on the temperature, one will expand more than the other one, which might trigger a switch that will cause the thermostat to either come on or go off, depending on which one you're doing. So that's what they're usually used in. So it will curve or move in one direction or the other. And if you look in the textbook, well, I'll just draw it out. But so in the textbook, here's your bimetallic strip, and then you'll have the other metal beside it. So when you wind up heating it up, what will happen is one thing might expand or contract more than the other. So you get a curve. So the blue might contract, and when it contracts, it's going to pull the red with it, and that pulling down is going to wind up triggering a switch or flipping a switch. So that's practical use of one of those. So it's usually a fairly small thing that happens. The expansion is usually pretty small, but even that small little expansion can play a huge role in things like railroad tracks and bridges. Okay, so those things are built to allow for that expansion and contraction. Otherwise, we can have buckling railroad tracks, which can cause trains to derail. We can have bridges that wind up collapsing because they don't have enough room for that expansion and contraction. So there's always going to be gaps in the railroad tracks and gaps in the bridges to allow for expansion, to prevent buckling and warping because of heat and cold constantly going back and forth and back and forth. It says the photograph below shows expansion joints between bridges, sections of a bridge. So that is page 353, that figure A at the top of the page. Okay, well, I guess that next page was the picture. Water has very special properties that set it apart from all other substances. And we've talked about these in chemistry, and we talked about in the biology. So this should be review, but we need to make sure we're aware of it. It is one of the big properties is its behavior at 4 degrees Celsius. If water is cooled below this temperature, it actually expands instead of contracts. And water is the only substance that does that expands when it cools instead of contracting. The expansion is due to, it says, microscopic clumps of crystalline ice between 4 and 0 degrees Celsius, which actually is caused by hydrogen bonding, if we remember our chemistry. So here's a water molecule. Here's another water molecule. So this hydrogen is a positive charge, partial positive charge. That's a partial negative charge. They are attracted to each other. Okay. And when they cool down, they are able to move closer together, and that hydrogen bonding becomes stronger. And so they don't line up side by side because that attraction between the positives and negatives kind of keeps them a little bit at a distance because that attraction is so strong, and it makes them expand rather than contract. So this is to blame for bursting water pipes in the winter. It's also the reason that ice floats. Okay, so and we have life in bodies of water even in the wintertime because ice floats. If it gets really cold outside, you want to make sure that you leave that faucet dripping just a little bit, because if that water freezes in there, then your pipes are going to burst. So you want to make sure they're well insulated. You want to leave that water running just a little bit so that it doesn't freeze solid and burst your pipes. That's usually a bigger problem in older homes, but it can happen in new homes as well. All right, so there are several ways in which energy can be added or removed from an object in order to change its temperature. So we're going to talk 3 things. We're going to talk about conduction, convection, and radiation. So this is the way that we can add heat, add energy, or remove energy. Okay, when one end of an iron rod is held in a fire, it doesn't take long before the other end becomes warm. If you leave a metal spoon in your pot as you're cooking, that spoon is going to heat up. That is called conduction. It's thermal energy transfer that occurs when higher energy particles collide with lower energy particles, transferring their kinetic energy. So they have to be touching. That's the big thing about conduction, is that the 2 things have to touch each other, okay, for that to happen. Okay. So the next is convection. And this is where we transfer thermal energy due to physical movement of the material. So you're moving the hot air around something. That is convection. Convection differs from conduction in that the transfer of thermal energy through physical movement from one place to another, rather than between the particles vibrating or touching each other in place. So in a convection oven, you'll notice there's a fan at the back, and that fan is going to push the hot air so that it completely circulates the food. And it's not that, and it's supposed to cook it more evenly, so that normally you don't have that fan there. So the things closest to the eye are the things touching, closest to the eye are going to have the most heat because they're in the closer proximity. But with convection, that hot air, it's not just about what's on the eye or the heating element. It's what the air that gets rotated around the material and cooks it faster and cooks it more evenly is the big thing. So portable electric heaters warm a room through convection. So it's pushing that hot air around and circulating that hot air. Heaters set up a circulating flow of air that transfers thermal energy from the heating coils to the air throughout the room. So it's not just that little bitty area closest to the heating coils, or if you have to be touching the heating coils. It blows that air, sends that air out to circulate in the whole room. So a lava lamp offers a nice visualization of convection because it is the actual moving. So when it heats up, that heated blob of oil at the bottom expands and becomes less dense, and so it circulates up and around. So that's a good visual of convection. And I think those are just diagrams that for some reason aren't showing up. All right. So the next one is radiation. Okay. So the warmth you feel of the sun is due to the light and infrared waves that it emits. These waves are electromagnetic waves. So they carry energy, their energy. They carry energy from the sun through space to the earth. The transfer of thermal energy in the form of electromagnetic waves is referred to as radiation. Okay, so it's not just touching, it's not just circling the air around it, it's an actual electromagnetic wave that comes a lot of times from a long, long way away and heats it up by the energy that wave holds. Okay, since radiation includes visible light, it is often possible to see the temperature of an object. So like a heating coil turns red. Okay, so a heating coil at 800 degrees Celsius is red. The filament in an incandescent light bulb is yellow. and that's about 3,000 degrees Celsius. Stars that are 30,000, sometimes they'll be blue. A flame can change colors depending on the intensity of the radiation in that flame. Okay. No, actually, the flame analogy is not a good one because that's dependent on the amount of oxygen that's there. So at one time, it was believed that an object contained a certain amount of heat fluid. Oops, this is heat capacity, which I think is starting the next chapter. It is, or the next section. But at one time, we didn't understand that heat was energy. We didn't really know what energy was. But we know it moved and it flowed. So we called it a heat fluid, or the word caloric. And we thought that it would flow from one place to the other. And that's where we get, eventually you'll learn that's where we get the term calories for energy, is we get it from that term caloric, which is what we used to think of when we talked about heat moving or flowing. Okay. All right. So that's all we'll do on that. We'll come back and have another video for 10.3. All right. So if you have any questions about, so we talked about the three ways that we can transfer energy through conduction, convection, and radiation. So make sure you know what those terms are and what they do. We learned that things expand as they are heated up, and that every object or every substance has its own coefficient of thermal expansion. So it expands differently depending on what substance it is. And we can calculate the change in the length of something based on its initial length, its coefficient of thermal expansion, and the change in temperature. Okay. All right. So any questions, please bring them to class and we'll discuss them as we do our practice problems.